Alright guys, so this is me just doing your 50 questions put up by Sethi. You can use this as a guide, and I'll tell you right off the bat that do not look at this just to get your answers. That's not the way to go. This class is practice, 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 so you should be doing the questions first, and then if you don't understand a specific question or an answer, you can look at this for how I would do it. So, starting from the beginning, our first question is this. The reagents are HBr, so this is technically over CH2Cl2. Our answer should be where we add a H and a Br. This is a Markovnikov reaction. It's hydrohalogenation, so what should happen is you should put the H on the less substituted side and put the positive on the more substituted side, like this. At this point, you can do a rearrangement, which is this H moves over here. Once you do that, you'll end up getting this. So this wedge stays, and then once we move the H, we'll get a positive at this spot right there. After getting that positive, your Br can attack, but it can attack wedged or dashed, and because of that, we get two answers here. So this could be the answer, plus the other answer would be if it came from the back, from the front, which would be this answer. To figure out if you made enantiomers or diastereomers, just do your R and S. So over here, we should get this as your number 1 party, number 2, and number 3. So here I'm S on this carbon, so this will stay S also. And on this carbon, I have 1, or this atom, we have 1, 2, and 3. So I'm also S, but I'm going to flip because Br is on the back, so this one's R. And then over here, this one will be S. So if you remember from exam 1, this is SRSS, so these are diastereomers of each other. Okay, next question, we're again, double bond reaction. We're adding a H and a OH, but notice that the OH specifically went on the less substituted side, which is anti-Markovnikov. So this is your hydroboration, BH3, THF, I believe NaOH, H2O2, water, all of that. And then it has a 1 and a 2. So something like that. Okay, next question, we're adding a OCH3. So that's the same thing as adding a OR. We learned that whenever you can add OH, you can also do OR. Just change your thing. Instead of having a water, you just have an alcohol. At this point, notice this was my double bond, but the ending thing went over here. So that means a rearrangement happened, and rearrangement's only going to occur if I do H2SO4, so if I do hydration. So if I do H2SO4, that puts a H at that spot, and we get a positive here. Then we're going to rearrange by moving this H, and then put my OCH3 there. So I know it's H2SO4 over CH3OH. because I want an OR at the end. Next reaction, I'm already seeing a double bond next to a cyclic structure that is not a 6-carbon ring, so I'm thinking ring expansion. And that's exactly what's going to happen here. You're going to start off with putting the H at the end, getting a positive, and then you do a ring expansion. This is going to end up making a cyclopentene with a positive here. Then you do another rearrangement until you get a tertiary positive, and then at this point you can attach your OH because we have water. Notice I don't have to write this as a wedged or dash because this is not a chiral center, so it doesn't matter. But that's your final answer. I'll box the answers. There you go. Next one. This one I'm adding a OR again and also an H. So again, H and an OR. But notice normally if I do this reaction, you should go put an H, get a positive, and then do a rearrangement. But that didn't happen. So the only reaction that stops rearrangement like that is it's oxymercuration. So HgOAC2, I think water, and then NaBH4. If the reagents are a little bit wrong, just pick the right one. Similar thing happened here. We again added a H and OH. Oh, really quick. We had an OR here, so we can't have water. We have to put an alcohol. Sorry. So this needs to be an ethyl, so you gotta have ethanol like that. Okay, now I have an H and OH. But similar thing. We didn't have a rearrangement. We should have had a methyl shift. We didn't. So this is just HgOAC2, but with water this time. Second part NaBH4. Okay, this one, again, we added a H and an OH. They didn't show it to us as being wedged or dashed, so I'm assuming it doesn't matter. They don't, or at least they don't care about it. All I can see is that the OH went on the less substituted side. So like before, this is hydroboration, BH3, THF, all that good stuff. NaOH, H2O2, water. 1 and 2. Okay, and this one I have a trans double bond in the beginning, and my reagents are Br2CH2Cl2, so I should be adding 2 Brs, and specifically they have to go trans to each other. So we can think of it as like this. Let's say our first Br goes in wedged, well then the second one has to go in as a dashed. Okay, and I could have gotten the other answer where the first one went in as a dashed. But before I do that, let's just figure out what the R and S would be. So for this carbon right here, I would get 1, 2, 3. So this is R. And for this carbon, I get 1, 2, 3, and I'm getting S. Okay, since I'm getting R and S on my 2 spots, we learned this from exam 1. There's 2 chiral centers, or allegedly there are chiral centers. They have the same substituents, but one is R, the other one is S. So that's by definition a meso compound, meaning it's achiral. So I don't have to draw the other answer. If you drew the other answer, you would just get SR, which is also a meso compound. Okay, next one is a cis double bond. So this one looks like this right here. We're gonna still stay true to what the reaction tells us to do, which is add my 2 things wedged and a dash. So let's say we add this one as a wedge, so this one will go dashed. But if we rotate around this single bond and make it go like up and down like that, well then they're going to be same. Because when they're cis, they're opposite. When you rotate around, you'll be the same like this. And now if we do R and S, well, I'm going to get both of them being the same. So if this one is 1, 2, 3, S, this one's also going to be 1, 2, 3, S. So since they are both S, that means we created one of the enantiomers, and if I did the answer as both dashed, that would be the RR answer. So it's this answer plus the other answer, which is where they both go dashed. Like this. And this one would be R and R. So I know I created enantiomers here. Alright, next question, we added a BR and an OH. The OH went on the more substituted side, which makes sense. They again didn't show the wedge in the dash. They probably should have, but it's okay. But the only reaction that adds a BR and OH is Br2 with water. Next one, it's the same thing as last time, except instead of having water, I have an alcohol. But we're gonna literally just do the same thing. Let's imagine that the first thing went in as, let's say the Br went in as a wedged. Well then, when the CH3OH attacks, it would have to come in as a dash. So if I can give you an example, so this is what my Br would look like when it comes in, and then the CH3OH can come in over here from the back. So in the end, I should get something like this, where this is my CH3OH, there's a wedged methyl there, and then there's a wedged Br there. Now the other answer would be if I came in from the other side. So you get this plus the other answer where the original Br came in as a dashed. So then this one would have to come in as a wedged. Here, I'll keep it consistent so you don't get confused. So this one would be the CH3OH, and then this methyl has nothing to do with anything. But you would get these 2 answers. Okay. This one has just H+, which, okay, what is this one? Let me think. I think this is, I'm surprised she only kept it as H+. I guess she wanted H+ over water. I'm not sure. I'm doing this live too, so I'm not sure either. But if it's just H+, assuming it's over water, well, that's just hydration, and you would just end up with the OH. Now, because it's completely symmetrical, this can technically happen on either one, so I guess maybe she wanted you to overdo the reaction like that. I would guess this is the answer, if that's my best guess. Again, it would just be put an H, get a positive, and then I'm assuming there's water, so water attacks, and then you deprotonate. But it happens twice because both of the double bonds are the same. That's my best assumption for what she wanted. Next one is a triple bond reaction, and as you can see in this one, I kept the double bond, so what happened was I added this Br and this Br, so only two Brs got added. Well, we know that reaction, that's Br2CH2Cl2, and this was one equivalent because we only did it once. In this one, we added an H and a Br, so that one would be one equivalent, HBr with CH2Cl2 or CCl4. For all of these, you can do CCl4 also. Okay, this one is CH3Cl3. This was one of those weird reactions, in my opinion. So this one will be you making the the carbene. So we're gonna draw it like this, CCl2. Now, if you don't like that, you can also just go like this, and then this is your cyclopropane thing. Now, it's easiest if we just write it like this, and that's how they're going to probably write it, where you just make one of these wedged and one of these dashed. But all you make is that little carbene thing, which eventually we end up making one of these, C with two Cl's, and then a lone pair. So this is going to attack it, this attacks it back. Next one, we have a CH2 now. So this was the reaction where you can do it two ways. I give you two sets of reagents. For us, let's use ZnCu over something. Now, I don't exactly remember what it was, but I remember the other set of reagents were, all this makes is CH, that carbene, and then you attack it, and this attacks it back. It's in the notes. I don't remember the exact reagents, but it's something with ZnCu. The other reagents were, I believe, H2, I think it was H3CN2, I believe, with a strong base. So this looks like this. A strong base took the H off, and then the N2 gas left to make your CH2 with a lone pair. So look in the notes for my class to figure out what the exact reagents were for this. But this was also part of those weird reactions. Okay, moving on, next reaction is a triple bond reaction. I don't believe we went over this reaction in class, which is unfortunate, but I'll go over it in next class. This is one of those reactions that's an oxidation reaction. So what you're doing is, if you ever have a terminal triple bond and you're making an aldehyde, so you're making the little ketone at the very end, that reaction is the one that goes BHCO2. Okay, the way that works is you're going to take the triple bond and you're going to make it look like this, and then you do the little ketone to enol to make your aldehyde like that. So it's BHCO2. There's other stuff there, I think, like THF, H2O2, NaOH, all that stuff. So make sure rest is right. But the first part is Cl. So you always use the Cl one if you want the aldehyde at the end. Okay, if you want the ketone at the end, well, that's where you use the other one, which is just BH3 with THF and so on and so forth. Okay, and this one's going to make this instead. You make the alcohol in the middle like that, and then you do ketone to enol to make it into that. Awesome. So this reaction, next one, is how to make a double bond go into a triple bond. Well, since we're adding more bonds, we know this has to be an elimination reaction. So this is actually not just one step, it's actually two steps. The first part is to do Br2 over CH2Cl2, and then the second part is to do 2NaNH2 over NH3. So what's happening here is you're taking your double bond, and you're first turning it into two Brs that are anti to each other, like this. And then at that point, NaNH2 acts like a elimination step, because what you're doing is you're taking an H like this, and then this goes here, making this Br leave, right? And then you have another NH2, which is going to take this H, and this one goes here, and then this Br leaves, thereby giving you the triple bond. It's 2 eliminations in 1 step. So this is not going to change. All right. So before we had triple bonds at the very end. If they're at the end, you want to use the BH3 reaction like that. But if you're ever in the middle, well, technically both of these sides are the same. It doesn't matter. Even if I added carbons here, they're still considered the same. And for this question, what we, and also we're making a ketone, the reagents they'll end up using is Hg, actually I think it's, yeah, it is HgSO4 over H2SO4. This one is also another ketone to enol, so it makes it into like this. Or you make the other one where it's over here, but they're both the same thing right now. So I'm just going to erase the bottom one. And this does ketone to enol to make our final answer, which is drawn. So you can either make it there, but with ours we would make this, but this is named the same, so you can go either way. Next one is a reaction now using dienes. This one is specifically, first we have to pick whichever double bond is more reactive, and then we can go on with the reaction. Now notice I have 2 pathways again. I know I'm not going to put the H in the middle because we said in class. So if I put the H over here, then I get a secondary positive. If I put the H on the other side, I get a tertiary positive. So because of that, the more reactive double bond is the bottom one, and that's the one we're going to use. Again, that has nothing to do with kinetic or thermal right now. It's just picking the correct double bond. So they didn't say heat or kinetic here, so I guess I'll give you both. If we do the bottom one, which is the one we need, we'll end up making this as our intermediate. And at this point, my Br can attack, or I can do a resonance and then it attacks. So notice if the Br just attacks at this point, I would get this. The other answer would be if I had resonance first, well then this would have went here. If it goes there, I would get this as the answer. So luckily for us, both of the answers are the same thing. If you try to name them, they're exactly the same thing. Because they're the same thing, it doesn't matter which one I make, and that's why she didn't write kinetic or thermal, because regardless of what you make the same thing. Next one, we're going to use the same logic. You're not putting the H in the middle like that. If I did the H over here, I would get a tertiary positive. If I did the H on the other side, I would get a secondary positive. The better one is the tertiary positive, so that's the one we're going to do. So one answer would be to put the H at the end, and then you put the Br here. And the other answer would be you do a resonance, and then you get the answer. But luckily here again, we're gonna do this resonance and get the same answer, so it doesn't matter. So look, if we get the double bond there, Br here, these are the same thing yet again, just like before. So the answer is actually exactly the same here. These two are the same. It just happens to be that. So there's no kinetic or thermal, but they're exactly the same. Oh, I'm sorry. I added a H and a Br here. That's not what they want. The answer would be the same if it was H and Br. We actually have a Br2. So that is not right. The real answer would be this. I know this is my double bond. We figured out that that's the more reactive one. So we just add 2 Brs. Whenever you're adding 2 Brs, there is no rearrangement whatsoever. There's no resonance, none of that. Because we're making the bridge, there's no positive. So it doesn't matter. We're turning our first intermediate. It kind of looks like this. Br positive, like that. There's no resonance here. So because there's no resonance, all you have to do is figure out that that double bond was more reactive, and then add your 2 Brs. That's it. So that should be the answer. Okay. Next one is a triple bond that ended up having 2 Brs put on it. So notice that they're specifically trans right now. So the way I can get that is first I have to make this into a trans double bond. If I can make it into a trans double bond, then they'll add in trans to each other, and then we'll be good to go. So this is a mini synthesis, I guess. Right before this, I know it looked like that. Here, let me draw that better. So right before this, I know it looked like that. And at this point, all we did was Br2, CH2Cl2 to add two Brs trans to each other. So how do you make trans double bond from a triple bond? Well, this reaction is 2Na over NH3. It's a chapter 11 reaction. I'll go over it in next class. But that's how you do it. So if you want to write it, you would just write Br2, CH2Cl2, and part 2 is 2Na over NH3. For this one, when they're the same, well, this is very similar to a question we did before, which was to make two BRs that are same with each other. And we noticed we needed a cis double bond, right, to get that answer. So because we want a cis double bond, I know that right before this, it looked like this right here. What happened to this? All right, I'm going to pause the video for a little bit.